Welcome back to Explaining Everything, the channel where we dive into the stories and mysteries behind everyday things. Today's question comes from one of our curious viewers, Ordinals. Thanks for the suggestion, Ordinals. You asked, why are some elements more radioactive than others? If you've ever heard about uranium, radon, or plutonium and thought, why are those the drama queens of the periodic table? You're not alone. Today, we're diving deep into atomic instability, nuclear forces, and why some elements just can't keep it together. So, if you've ever wondered why certain atoms go nuclear while others just quietly exist, you're in the right place. Right here on Explaining Everything. Every atom has a tiny, dense center called the nucleus. This is where protons and neutrons live. Protons have a positive charge, and neutrons are neutral, which makes them the Switzerland of the subatomic world, just vibing, not picking sides. Now, here's where it gets spicy. Protons don't like being near each other. Positive charges repel, so stuffing them together in a tiny space is like cramming a bunch of hyper-toddlers into a closet and hoping for silence. It doesn't end well. Thankfully, there's a thing called the strong nuclear force. This force is like the patient babysitter of the universe. It holds protons and neutrons together, overpowering their urge to fly apart. But it only works over super short distances, and it starts struggling the moment the nucleus gets crowded. In small atoms, the balance is great. Few protons, few neutrons, everyone's happy. But as you move up the periodic table and start stacking more and more protons together, the babysitter is outnumbered. Tensions rise, the strong force gets overwhelmed, and the atom starts to lose control. That's when you get radioactivity. Take uranium-238. This atom is big. It has 92 protons and 146 neutrons, basically the atomic equivalent of trying to seat an entire rock band and their entourage at a two-top table. Those 92 protons are constantly trying to push each other apart, while the neutrons are stuck playing mediator. But even with all those neutrons, the balance isn't quite right. The whole thing is unstable, like a poorly constructed Jenga tower. So uranium does what unstable atoms do. It breaks down. When uranium decays, it tosses out particles, alpha particles, beta particles, and sometimes gamma rays, in an attempt to reach a more stable state. It's like trying to calm down by throwing pieces of yourself across the room. Not the healthiest coping mechanism, but it works. Eventually. So, when we say some elements are more radioactive than others, we're really saying their nuclei are more unstable, and they're trying harder and faster to fix it. Now here's the real key to why one atom is stable and another is an explosive disaster. The ratio of protons to neutrons. In small atoms like helium or carbon, a 1-to-1 ratio works great. They're simple, stable, and not looking for drama. But as atoms get larger, they need more neutrons to counteract the increasing proton repulsion. Think of neutrons as nuclear bouncers. No charge, but they keep things from getting too rowdy. For example, lead, element 82, has 82 protons and 125 neutrons, and it's stable. It's reached the right neutron-to-proton ratio to hold things together without drama. But go just one step higher to bismuth, and things start to fall apart. If the neutron-to-proton ratio gets too far off, too many of one, not enough of the other, the atom becomes unstable. It's like trying to balance a pizza box on a broomstick. You might hold it for a second, but it's not going to last. Now that we know why atoms decay, let's talk about how fast they do it. That's where half-life comes in. The half-life of an element is the time it takes for half of a sample to decay. Some elements decay slowly, like uranium-238, with a half-life of over 4 billion years. Others are basically gone before you can blink, like polonium-214, which has a half-life of 164 microseconds. That's shorter than most people's attention spans. The shorter the half-life, the more radioactive the element is. That's because it's spitting out radiation faster. Its unstable nucleus is in total meltdown mode, frantically trying to stabilize. So when someone says something is highly radioactive, what they mean is that it has a short half-life and is actively disintegrating like a middle school group project under pressure. Here's a wild fact. Every element after bismuth on the periodic table is radioactive. All of them. No exceptions. That's because once you get past 83 protons, the nucleus becomes too large to hold together. Even with a boatload of neutrons, the strong force can't manage the chaos. These atoms are doomed to decay, some in seconds, some in years, but all of them eventually. And the really heavy, man-made elements, most of them last only milliseconds before breaking apart. They're like the mayflies of the periodic table, here for a good time, not a long time. In short, some elements are more radioactive than others because their nuclei are unstable. That instability comes from having too many protons crammed together, a bad proton-to-neutron ratio, or just being so massive that the strong force gives up and goes home. So now you know, radioactivity is all about nuclear balance, or the lack of it. Some elements are calm and collected, while others are ticking atomic tantrums trying to sort themselves out by blowing off particles. It's messy, fascinating, and very, very energetic. If you enjoyed this radioactive deep dive, give this video a thumbs up, hit that subscribe button, and don't be like uranium. Also, if you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for tuning in, and join us next time here in the channel that answers all the why, what, who, where, and how questions you've always wondered about, here on Explaining Everything.